A very good morning to you. Principles of Geochemistry, the structure and composition of atmosphere. Lecture 4. Topics to be covered are, there are so many definitions, significance of atmosphere, composition of atmosphere, then what's the difference between permanent gases and variable gases, vertical structure of atmosphere, origin of atmosphere, evolution of atmosphere, composition of primeval atmosphere, then what are the atmospheric additions during geologic time, and what are the atmospheric losses during geological time, and summary. Coming to the definitions. So what is atmosphere? Atmosphere, it can be defined as the thin envelope gases surrounding the earth, and it is highly compressible. The atmosphere is a layer of the gases that surrounds a planet, and these are held in place by gravity. In the context of the earth, it's a protective blanket of air which is composed of nitrogen, oxygen, which is essential for life and regulates the planet's atmosphere. The gases, droplets, and the particles surrounding the Earth's surface, it also includes the atmosphere. The atmosphere extends from the surface of the planet outwards, becoming thinner with the distance. What is climatology? Climatology is the science that studies the long-term atmospheric conditions. So this is nothing but the weather conditions averaged over a long period, usually 30 years or more. And it's a branch of atmospheric science that explores both past weather patterns and the current climatic variations to understand the long-term trends and the impact of any human activity on climate change. Coming to the air, air is a mechanical mixture of gases and aerosols. Air is the invisible, odorless, and tasteless gaseous mixture that surrounds the earth, and it is composed mainly of nitrogen and oxygen, and it's crucial for life, providing the oxygen that animals need to breathe and the carbon dioxide that plants need to live. Meteorology, the science that studies the atmosphere and its processes. It is a scientific study of the Earth's atmosphere and its phenomena with a primary focus on weather forecasting. It encompasses the observation, understanding, and prediction of atmospheric conditions and weather patterns. Meteorologists, they use various tools and techniques to analyze the atmospheric data and develop models for predicting the future weather. Then what is weather? Weather, it is defined as simply short-term atmospheric phenomenon or conditions. So weather is the state of the atmosphere, and it describes, as an example, the degree to which it is hot or cold, wet or dry, calm or stormy, clear or cloudy. Atmosphere is a layer of gases that surrounds a planet, and these are held in place by gravity. Earth's atmosphere is primarily composed of nitrogen and oxygen, with smaller amounts of other gases like argon and carbon dioxide, and it plays an important role in protecting life on the Earth by absorbing harmful solar radiation, regulating the temperature, and facilitating the water cycle. It balances the global temperature on the Earth, and it is made up of various gases like nitrogen, oxygen, carbon dioxide, water vapor, ozone, etc. Then why atmosphere is important, or what is the significance of atmosphere? Sunlight filtering through the clouds in the sky over an empty field. Earth's atmosphere is a thin blanket of gases and tiny particles, together we call as an air, and we are most aware of the air when it moves and creates wind. All living things, they need some of the gases in air for life support. Without an atmosphere, Earth would likely be just another lifeless rock. Earth's atmosphere, along with the abundant liquid water at the Earth's surface, are the key to our planet's unique place in the solar system. Atmosphere, it acts as a transporting medium for many geochemical reactions on the surface of the Earth, and it's an important part of many geochemical cycle of elements, and it is essential for a liquid phase, or this is also known as a hydrosphere, to exist. And it is indispensable for life of Earth and it is crucial part of the water cycle, and it moderates Earth's temperature. Composition of atmosphere. The composition of the atmosphere, it is crucial for life on the Earth, and it includes various gases like nitrogen, oxygen, argon, carbon dioxide, neon, helium, krypton, xenon, hydrogen, nitrous oxide. And nitrogen provides a stability and is a building block for life, while oxygen supports respiration and combustion. And carbon dioxide, though a small percentage, it is vital for photosynthesis and it helps regulate the planet's temperature through the greenhouse effect. Overall, we can say that the atmosphere is a mixture of gases and it constitutes microscopic solid particles, water droplets, and so on. There are types of gases like permanent and variable gases. Permanent gases means gases that form a constant proportion of the atmospheric mass. And variable gases means gases whose distribution in the atmosphere it varies both in time and space. Permanent gases are relatively stable and as such they have very long residence time. Due to long residence times, permanent gases constitute the bulk of the atmosphere mass. And these gases that form a constant proportion of the atmospheric mass, it includes nitrogen, oxygen, argon, neon, helium, krypton, xenon, hydrogen, and so on. And the variable gases means those gases whose concentrations change from time to time and from place to place. Some of these gases are important to weather and climate like water vapor, carbon dioxide, and ozone. Composition of the atmosphere, it includes mobile or fugitive elements that make up the atmosphere. Mean lifetime is mean or average time that a given molecule resides in the atmosphere. For nitrogen, the mean lifetime is roughly around 10 to 100 million years, whereas for the oxygen it is recycled every 2000 years, and for carbon dioxide, the mean lifetime is 30 years. Why nitrogen is inert means this is inert chemically, and nitrogen has molecular speeds too slow to escape to space, and it is not very soluble in water. As we have discussed, the mean lifetime is roughly around 10 to 100 million years. And nitrogen, it is the most abundant gas in the atmosphere as it is comprising about 78% because it is relatively unreactive and it has been released from the atmosphere over a long period, primarily through volcanic activity and the decay of organic matter. Unlike oxygen, which is consumed in various biological and chemical processes, nitrogen persists in the atmosphere due to its stability and lack of reactivity. And the amount of nitrogen being cycled out of the atmosphere, it was very limited, and nitrogen became the most abundant gas in the atmosphere. Coming to the oxygen balance it is regulated by the biosphere through photosynthesis, and oxygen it constitutes 21% of the atmosphere and it is important for plant and animal respiratory processes. It is also important to various chemical reactions, so especially oxidation that break down rock materials during chemical weathering. Without oxygen, things cannot burn either. So free oxygen in the atmosphere, it is a product of plant photosynthesis and plants take up carbon dioxide and in the process of photosynthesis, they release oxygen. And the main things are respiration and oxidation by decay. So excess oxygen, it is used in the burial of the organic matter. Carbon dioxide is supplied into the atmosphere by various processes like plant and animal respiration, the decay of organic material, volcanic eruptions, natural and anthropogenic combustion, and that's why the mean lifetime of carbon dioxide it is around 30 years. Carbon dioxide, like oxygen, is involved in photosynthesis, but the main process controlling its concentration in the atmosphere is its solubility and reaction with water. So carbon dioxide is much more soluble in water than oxygen and nitrogen. The proportional solubility of carbon dioxide, oxygen and nitrogen is 70 is to 2 is to 1. So most free oxygen and nitrogen are in the atmosphere, while most carbon dioxide it is in the oceans. In addition, much carbon dioxide is also tied up as calcium carbonate on the ocean floor, or it is also deposited as an ancient carbonate sediments on the land. Carbon dioxide in the sediment ocean atmosphere system, it buffers its content in the atmosphere to an essentially constant value. Variable gases. Water vapor is the most abundant variable gas. Water vapor is supplied to the atmosphere by evaporation from the surface, and it is removed from the atmosphere by condensation in the form of clouds and rains. So the concentration of water vapor is maximum near the surface and the tropics, and it decreases rapidly towards higher altitudes and latitudes. Water vapor is very important to climate because it is a greenhouse gas that can absorb thermal energy emitted by the earth, and it can release latent heat to fuel weather phenomena. Water vapor is considered as the most abundant variable gas in the atmosphere because its concentration changes dramatically depending upon the location and time, unlike other major atmospheric gases like nitrogen and oxygen, which remain relatively constant. While nitrogen and oxygen make up the bulk of the atmospheric composition, water's vapor's presence is highly dependent on temperature and available moisture sources. Ozone, it can be both good and bad depending upon its location in the atmosphere. Good ozone, it is located in the stratosphere, the upper layer of the atmosphere, and it absorbs harmful ultraviolet radiation from the sun and it protects life on the earth. Its concentration, that means it can reach 15 ppm at its peak in the ozone layer, and it is beneficial as it shields us from ultraviolet radiation, which can cause skin cancer and other health problems. Coming to the bad ozone, so this is located in the troposphere, the lower layer of the atmosphere where we live, and it's a component of smog and air pollution. Its concentration, even at low levels around 0.1 ppm, it can be harmful to the human health, especially for those with respiratory issues. And it can cause breathing problems, lung damage, and other respiratory issues. It forms through chemical reactions involving pollutants like nitrogen oxides and volatile organic compounds, especially in the presence of sunlight. Ozone forms through chemical reactions involving pollutants like nitrogen oxides and volatile organic compounds, especially in the presence of sunlight. And it protects from harmful ultraviolet radiation. The ozone layer absorbs most of the sun's harmful ultraviolet radiation, preventing these rays from reaching the Earth's surface. And it prevents skin cancer and other health problems. And excessive exposure to ultraviolet radiation can cause skin cancer, cataracts, and weakened immune systems in humans. And it safeguards marine ecosystems. Ultraviolet radiation, it can damage phytoplankton, which are the base of the marine food chain, and harm other marine organisms. And it supports terrestrial plant life. High levels of ultraviolet radiation can stunt plant growth, reduce crop yields, and even kill plants. And it helps maintain a stable climate. Ozone plays a role in regulating temperatures in the stratosphere, which can indirectly influence global climate patterns. Coming to methane gas. Methane is considered as a variable gas in the Earth's atmosphere. This means its concentration it can change based on location and time due to factors like human activities and natural processes. A variable gas in small but recently increasing concentrations, when once released into the atmosphere through fossil fuel activities, livestock digestion and agriculture cultivation, especially rice. It is a very effective absorber of terrestrial radiation, and it plays an active role in near surface warming. Other halogens includes fluorine, bromine, and iodine. They have also been detected in the atmosphere, and fluorine is probably put into the atmosphere as an industrial contaminant, which is liberated by burning of fuel and calcination of material containing fluorine are released in the manufacture of phosphatic fertilizers from rock phosphates, which always contains some fluorine-bearing apatite. And this fluorine has also been released through volcanic activity, and bromine and iodine, they are released into the atmosphere in very small variable amounts. Other atmospheric constituents, it includes aerosols and air pollutants. Aerosols are fine solid or liquid particles suspended in the air, and they play a significant role in the Earth's climate and atmospheric processes, acting as cloud condensation nuclei and influencing the amount of the sunlight reaching the surface. Air pollutants are substances in the air that can be harmful to human health and the environment. Common examples include particulate matter, ground level ozone, carbon monoxide, sulfur dioxide, nitrogen dioxide, and lead. And these pollutants can be released from both natural sources like volcanoes and wildfires, as well as human activities such as burning fossil fuels and industrial processes. The atmosphere is divided into main regions based on the uniformity of its chemical composition, the homosphere and the heterosphere. The homosphere, extending up to about 80 to 100 kilometers, has a relatively uniform mix of gases like nitrogen and oxygen. Above this, the heterosphere, it exhibits a layered structure with varying gas compositions. Homosphere, it includes troposphere, stratosphere, and mesosphere. Convection currents are prominent below 60 kilometers, and layer below 60 kilometers is the homosphere. And geochemistry of atmosphere concerns mainly with this region, and physical and photochemical reactions that takes place at around 60 to 100 kilometers, and at 240 kilometers atomic oxygen is predominant, and at higher elevations helium and hydrogen are predominant. Coming to heterosphere, it has a layered composition. Above the homosphere, the heterosphere, it exhibits a layered structure with distinct variations in the composition of gases. In the heterosphere, gases are separated by diffusion, with the lighter gases like hydrogen and helium found at higher altitudes. This is known as a diffusive separation. And the heterosphere, it begins around 80 to 100 kilometers and extends outwards into space. This is the altitude range of the heterosphere. And atmosphere formed by heating and differentiation, and it includes thermosphere and exosphere. Atmosphere formed by heating and differentiation, it includes 4 different steps. And the early Earth's atmosphere formed through a process of heating and differentiation, where volcanic outgassing, it has released trapped gases from the planet's interior, and subsequent heating and cooling cycles which have influenced the atmospheric composition. This initial atmosphere was very different from today's, primarily composed of water vapor, carbon dioxide, sulfurous gases, and nitrogen. Atmosphere, it has formed by different processes, like different steps involved. Step 1, it includes the primordial or ancient gases which have lost to space due to solar winds. And step 2, it includes the volcanic venting and icy comets. They release carbon monoxide, carbon dioxide, ammonia, methane, and water vapor. And the third step, it includes the steady addition of gases from volcanoes, which builds up the volume of the atmosphere. And the step 4 includes the blue-green algae convert carbon dioxide to oxygen. Coming to the layers of atmosphere. So this constitutes troposphere, stratosphere, mesosphere, and thermosphere. Troposphere, it contains 80% of all air, and stratosphere, it absorbs ultraviolet radiation, and ozone is present in this layer. And mesosphere, it protects Earth from the meteorites, and the thermosphere, most meteorites burn up here. The vertical structure of the atmosphere, the layers in the atmosphere, they vary with the density, chemical composition, electrical characteristics, and temperature. Coming to the troposphere is the lowermost atmospheric layer, and it is the atmospheric layer between the Earth's surface and an altitude of 8 kilometers at the poles and 18 kilometers at the equator. The thickness is greater at the equator because the heated air rises to greater heights, and the troposphere ends with the tropopause. And temperature in this layer, as one goes upwards, it falls at the rate of 5 degrees centigrade per kilometer. and it reaches minus 45 degrees at the poles and minus 80 degrees centigrade over the equator at tropopause. The fall in the temperature is called as a lapse rate. The troposphere is marked by temperature inversion, turbulence, and eddies. It is also meteorologically the most significant zone in the entire atmosphere. Almost all the weather phenomena like rainfall, fog, and hailstorm, etc., are confined to this layer. It is also called the convective region since convection stops at tropopause, and the troposphere is the theater of weather because all cyclones, anticyclones, storms, and precipitation occur here, as all water vapors and solid particles lie within this. And the troposphere is influenced by seasons and jet streams. Tropopause is the topmost layer of the troposphere, and it acts as a boundary between the troposphere and the stratosphere. And this layer is marked by constant temperatures. Coming to the stratosphere, it lies beyond the troposphere up to an altitude of 50 kilometers from the Earth's surface. The temperature in this layer remains constant for some distance, but then rises to reach a level of 0 degrees centigrade at 50 kilometers altitude. This rise is due to the presence of ozone. So, harmful ultraviolet radiation is absorbed by ozone, and a temperature inversion in the stratosphere, it is characterized by increasing temperature with altitude, unlike the troposphere, where the temperature typically decreases with altitude. This occurs because the ozone layer in the stratosphere, it absorbs a significant amount of ultraviolet radiation from the sun, heating the upper layers and creating a temperature inversion. In the troposphere, the lower layer of the atmosphere, temperature generally decreases with increasing altitude. This is the normal lapse rate. Compared to the troposphere, the lower stratosphere, it experiences less turbulent air due to reduced convection, the vertical movement of the air in the atmosphere. This region is where the commercial passenger aircraft fly, and unlike the troposphere, the temperature begins to increase, the altitude increases within this layer. It is largely due to the presence of ozone layer, which absorbs and protects the Earth from the sun's ultraviolet radiation. This layer is almost free from clouds and associated weather phenomenon, making conditions most ideal for flying airplanes. So airplanes fly in the lower stratosphere, sometimes in upper troposphere where weather is calm. Sometimes cirrus clouds are present at lower levels in this layer. Mesosphere is an intermediate layer beyond the ozone layer, and it continues up to an altitude of 80 kilometers from the Earth's surface. So it extends from 50 kilometers and above the Earth's surface up to 85 kilometers. And this is mainly composed of extremely low densities of hydrogen, helium, and several heavier molecules, including nitrogen, oxygen, and carbon dioxide. There is a little ozone to absorb solar energy in the mesosphere, and therefore the air temperature in the mesosphere, it decreases with the height. Air molecules are able to lose more energy than they absorb, and this cooling effect, it is particularly large near the top of the mesosphere. So mesosphere, it receives less solar radiation than the layers above it, and the air is less dense than the layers below. Coming to thermosphere. Thermosphere lies between 85 kilometers and 600 kilometers. In thermosphere, temperatures rises very rapidly with increasing height. This layer helps in radio transmission, and in fact, radio waves transmitted from the Earth are reflected back to the Earth by this layer. As this layer has a low air density, the absorption of small amount of solar energy can cause large temperature increase. And the air temperature in the thermosphere, it is affected greatly by solar activity. The International Space Station and satellites orbit in this layer. Though temperature is high, the atmosphere is extremely rarefied. That means gas molecules are spaced hundreds of kilometers apart. So hence, as a result, a person or an object in this layer does not feel the heat. And person would not feel warm because of the thermosphere's extremely low pressure. And also, auroras are observed in lower parts of thermosphere. Ionosphere is an electrified region within the upper atmosphere where large concentration of ions and free electrons exist. This layer is characterized by ionization of atoms. Because of the electric charge, radio waves transmitted from the Earth are reflected back to the Earth by this layer. And temperature again starts increasing with height because of the radiation from the sun. So it has practical importance because it influences, for example, radio propagation on the Earth. And the ionosphere is a region of the atmosphere that is ionized by solar radiation, and it is also responsible for auroras. And most of the ionosphere is in the thermosphere, and the ionosphere plays an important role in radio communication. This ionosphere, it starts from the Earth about 60 kilometers above the Earth's surface and extends upward to the top of the atmosphere. Exosphere is the interface between the Earth and the space. And in this layer, the atoms and molecules escape to space, and hence the exosphere, the external or the outermost layer of the atmosphere. And this layer, it is in between approximately 600 kilometers to 10,000 kilometers above the surface. And here, very light gases are traced, and they are hydrogen and helium, and their molecules are spaced very widely. Coming to the evolution of the atmosphere, this can be read under different headings like the number one, the composition of primeval atmosphere. Number two, additions during geological time. And number three, losses during geological time. The composition of primeval atmosphere. The Earth's atmosphere originated from the gases released by volcanic activity as the planet has cooled after its formation. And this process is known as outgassing or degassing. It involved the release of water vapor, carbon dioxide, and other gases from the Earth's interior. Over time, the atmosphere has evolved through various stages, including the formation of oceans, the trapping of carbon in the carbonates and organic matter, and the eventual rise of oxygen through photosynthesis. Then what happened to this water? In the early Earth's atmosphere, much of the water vapor initially present eventually condensed as the planet has cooled, forming the oceans. Then this volcanic degassing, it has released significant amounts of water vapor, but this was a temporary phase. As the surface has cooled, this water vapor condensed into clouds and then rain, leading to the formation of the oceans. And the concentration of water vapor in the atmosphere, it was substantially reduced. Then coming to the formation of ozone. In the Earth's early atmosphere, the formation of ozone, it was a crucial step in creating a habitable planet. And this process was driven by the sun's ultraviolet radiation and the presence of oxygen, which has ultimately leading to the development of ozone layer, which shields the Earth from the harmful ultraviolet radiation. With oxygen emerging as a major component of the atmosphere, the concentration of ozone has increased in the atmosphere through a photodissociation process. And the carbon dioxide, it was gradually removed from the atmosphere through various processes such as the dissolution in the oceans and the chemical reactions with the surface rocks forming carbonates. And oxygen rise, the emergence of the photosynthetic life, particularly blue-green algae, that is cyanobacteria, led to the production of the oxygen as a product of photosynthesis. In the study of the composition of the primal atmosphere, comparison of atmosphere of the Earth and Venus, it will be of great help. By taking all of the carbon and nitrogen of the sedimentary rocks of the Earth's crust and adding them to the atmosphere as carbon dioxide and molecular nitrogen, when this is done, then we can show that the mass of the atmosphere may be increased 6 to 22 times, and that, like the atmosphere of Venus, like carbon dioxide would now make up about over 90% of its mass. And the overall similarity between the Venus and Earth, they share a chemical history with respect to fugitive elements. And high carbon dioxide in the Venus, it has an important role in the greenhouse effect. And as the high surface temperature, it will prohibit the condensation of water and the control of carbon dioxide by the solution of carbon dioxide in hydrosphere as the precipitation of the carbonates. Atmospheric conditions during geological time can be studied with the 6 of the following points. So number one, gases released by the crystallization of magmas, and number 2, oxygen, which is produced by photochemical dissociation of water vapor, and oxygen produced by photosynthesis, and number 4, helium from the radioactive decay of uranium and thorium, number 5, argon from radioactive decay of potassium, and number 6, gases added by solar wind, comets, and meteorites. Coming to gases which are released by the crystallization of magma. During the crystallization of magma, in the several stages, gases are released, and the most abundant is water vapor, followed by carbon dioxide and sulfur gases like sulfur dioxide, hydrogen sulfide, etc. And other gases, including hydrogen chloride and hydrogen fluoride, it may be also be present in very small amounts. How has oxygen as produced by photochemical dissociation of water vapor? Photochemical dissociation of water vapor, which is driven by ultraviolet radiation, it is a process that splits water molecules into hydrogen and oxygen. And this process, it occurs in planetary atmospheres, and it is a potential source of the atmospheric oxygen. So the oxygen, it is produced by photochemical dissociation of water vapor. Then how did the oxygen has come from? So this oxygen is produced by photosynthesis, and photosynthesis, it was the primary process to increase the amount of oxygen in the atmosphere. And the primitive forms of life in the oceans, they began to produce oxygen through photosynthesis. It has probably occurred 2.5 billion years ago. With the concurrent decline of carbon dioxide, then the loss of carbon dioxide was removed from the atmosphere through the dissolution in the oceans and chemical reactions with surface rocks forming carbonates. And the oxygen has become the second most abundant atmosphere after nitrogen. And banded iron formations and red beds have also increased the amount of oxygen. The oxygen produced by photosynthesis, it has reacted with the dissolved iron in the oceans, forming iron oxides deposits. These are also known as a banded iron formations before it could accumulate in the atmosphere. And red beds also plays a crucial role. After the ocean's iron was depleted, oxygen began to accumulate in the atmosphere, reacting with the iron on the land to form red sedimentary beds. These are also known as red beds, indicating a significant increase in the atmospheric oxygen. Helium liberation from the radioactive decay of uranium and thorium. The quantity of the helium which is liberated by radioactive decay during geological time is greater than that it is now present in the atmosphere. Release of argon from the radioactive decay of potassium. Then how the argon has come from means argon has three isotopes like argon 36, argon 38 and argon 40. Argon 36, it has an abundance of 0.307 and argon 38 has an abundance of 0.061 and argon 40, it has the highest abundance of 99.362. So that's why argon 40 is by far the most abundant of all the other isotopes like argon 36 and argon 38. The amount of the argon on the earth is anomalously high when it's compared with the other inert gases. This is due to the production of argon by the radioactive decay of potassium 40 throughout the geological time. And radioactive decay in the planet's bedrock, it has added argon to the evolving atmosphere. And much of the argon that is occluded in the potassium minerals and it has liberated into the atmosphere. Then how the gases are added by the solar winds, comets and meteorites? Gases in the solar system are added through various sources, including the solar wind, comets and meteorites. This we have already discussed what is a meteorite and then comets and then solar system and the composition of the solar system. The solar wind, it primarily contributes the ions and the electrons, while the comets, they contribute a mix of gases and dust through their outgassing processes. And meteorites, they also have added significant amounts of uh, primordial gases like helium, neon, argon, krypton, and xenon. Then atmospheric losses during geological time, it can be read under 5 different points. So these are number 1, loss of oxygen by oxidation to water. And number 2, loss of carbon dioxide by the formation of coal, petroleum, and disseminated carbon. And number 3, loss of carbon dioxide through calcium and magnesium carbonates. And number 4, loss of nitrogen by oxides of nitrogen, nitrifying bacteria. And number 5, loss of hydrogen and helium by escape from the earth. Then coming to the first point, like loss of oxygen by oxidation to water. Weathering can indeed remove oxygen from the atmosphere primarily through chemical weathering processes, specifically oxidation. This occurs when oxygen reacts with minerals in rocks, forming oxides or hydroxides. For example, iron-rich minerals oxidize, creating rust, or this is also known as iron oxide, which is a common reddish or yellowish coating on rocks and soils. This process consumes oxygen, effectively removing it from atmosphere. So iron is the principal consumer of oxygen during weathering, and manganese is converted from bivalent to quadrivalent stage. And oxidation, it converts sulfides into sulfates, or this can also convert into free sulfuric acid. And principal consumption of free oxygen, it is through oxidation of volcanic gases and hydrogen. Then loss of carbon dioxide. The loss of carbon dioxide, the atmospheric carbon dioxide, it can be lost through its reaction with calcium and magnesium carbonates, forming calcium and magnesium bicarbonates, which are soluble and they can be leached away from the soil or dissolved in water. This process, called the mineral carbonation, it can be a way to remove carbon dioxide from the atmosphere, but can also lead to the loss of soil carbonates. And the large amounts of carbon dioxide, must have been recycled from the magmatic sources throughout the geological time to maintain organic activity. And loss of carbon dioxide, it also lead to the calcium and magnesium carbonates. As more carbon dioxide has been removed as limestone and dolomite than as coal or other organic carbon. So mineral carbonation, it plays an important role. And carbon dioxide in the atmosphere can dissolve in water, forming carbonic acid. This acid can then react with the calcium and magnesium carbonates like limestones and dolomites, or with the calcium and magnesium bearing minerals in rocks, converting them to soluble bicarbonates. This reaction, it can lead to the formation of carbon dioxide from the atmosphere as the carbon is locked into the bicarbonate form. And the carbonate loss from the soil. This can be through leaching. The soluble bicarbonates formed during mineral carbonation can be leached away from the soil by rainwater, effectively removing the carbon from the soil ecosystem. And it has a global impact like carbon sink. Mineral carbonation, especially in certain geological formations and through enhanced weathering techniques, it is being explored as a way to sequester carbon dioxide and mitigate climate change. Then loss of nitrogen by oxides of nitrogen, nitrifying bacteria. Nitrogen is removed from the air through organic and inorganic processes. Organic processes includes nitrogen fixing organisms, soil organisms, and blue-green algae or cyanobacteria. And inorganic processes includes production of oxides of nitrogen by electrical discharges and photochemical reactions in atmosphere. The amount of the organically fixed nitrogen, it exceeds that has formed or fixed by inorganic processes. Hutchison in 1954 has proposed the geochemical cycle of nitrogen. Nitrogen is returned to the atmosphere by decay of organic matter. Then coming to the fifth point, like loss of hydrogen and helium by escape from the earth. The loss of gases by escape from the earth or any other planet, it depends upon gravitational field and mean square velocity of the gas molecules. The mean square velocity is the velocity whose square is equal to the mean of the squares of individual velocities, and it varies inversely as the square root of the molecular weight of the gas and directly as the square root of the absolute temperatures. At 0 degree centigrade, mean square velocity for hydrogen is 1.84 kilometers per second, and for helium it is 1.31 kilometers per second, and for water vapor it is 0.62 kilometers per second, and for nitrogen it is 0.49, and for oxygen it is 0.46, and for carbon dioxide it is 0.39, and at 100 degrees centigrade, these velocities increase by 17%. Coming to the summary, the gases that envelop and surround the Earth make up our atmosphere. Atmosphere, it acts as a transporting medium for many geochemical reactions on the surface of the Earth, an important part of many geochemical cycle of elements, and it is essential for a liquid phase or hydrosphere to exist. There are permanent gases and variable gases. Permanent gases are the gases that form a constant proportion of the atmospheric mass, like nitrogen, oxygen, argon, etc. And variable gases, gases whose distribution in the atmosphere varies in both time and space, like water vapor, carbon dioxide, and ozone, etc. Homosphere is the region within around 80 kilometers of the Earth's surface where there is chemical homogeneity, and heterosphere, it is located above the homosphere where lighter gases become more dominant with height. And layers in the atmosphere varies with density, chemical composition, electrical characteristics, and temperature. Layers in the atmosphere include troposphere, stratosphere, mesosphere, thermosphere, ionosphere, and exosphere. Evolution of atmosphere, it can be dealt with the composition of primeval atmosphere, which is conditioned largely by the mode of origin of the Earth and its very early history, planetesimal hypothesis, and the interior of the Earth. Then additions during geological time and losses during geological time. Then what are the atmospheric additions during geological time? So number one, gases released by the crystallization of magmas. Number two, oxygen produced by photochemical dissociation of water vapor. Number three, oxygen produced by photosynthesis. And number four, helium from the radioactive decay of uranium and thorium. And number five, argon from the radioactive decay of potassium. And number six, gases which are added by the solar wind, comets, and meteorites. Then what are the atmospheric losses during geological time? So number one, loss of oxygen by oxidation to water. Number two, loss of carbon dioxide by the formation of coal, petroleum, disseminated carbon, and so on. Number three, loss of carbon dioxide by calcium and magnesium carbonates. And number four, loss of nitrogen by oxides of nitrogen, nitrifying bacteria. And number five, loss of hydrogen and helium by escape from the earth. So these are the references, and hope you can explore geosciences. Thank you for your time. See you in the next video.